work, energy, power. We throw these words around all the time, right? But what do they actually mean in physics? Well, it's probably not what you think. Let's dive in and break down what they're really all about. And trust me, it might just change how you look at, well, everything.
So let me start with a question for you. Right now, as you're watching this, you're focused, you're concentrating, you're learning. You'd definitely say you're working pretty hard, wouldn't you? In everyday life, for sure. But in the world of physics,
Yeah, you're not doing any work at all. Kind of weird, right? And that's because physics has this super specific set of rules for what counts as work. And spoiler alert, it has absolutely nothing to do with how much you're thinking.
All right, so let's get into it. For a physicist, work isn't about breaking a sweat or feeling exhausted. Nope. It all comes down to two very specific things happening at the exact same time.
So here's the deal. For work to happen in physics, you need two ingredients. First, a force, a push or a pull. And second, displacement. The object has to actually move because of that force. So think about it. If you go and push against a brick wall with all your strength, you'll get tired, you'll feel like you've done a ton of work. But if that wall doesn't move 1 single inch, in physics terms, you've done zero work. Zilch.
And this is where it gets really, really cool. The formula isn't just as simple as force times displacement. There's this secret ingredient, this third piece of the puzzle that has to do with the angle of the force. You can almost think of it like an effectiveness score. It tells you how much of your push is actually helping the object move forward. And as you're about to see, that angle changes everything.
Yeah, because of that little angle in the formula, work isn't just a simple yes or no deal. It can actually be positive, where it helps things move. It can be negative, where it works against the motion. And get this, it can even be zero, even when there's a force and the object is moving. So how does that work? Let's check it out.
Okay, this leads us to one of the most classic physics head-scratchers of all time. Picture this. A porter is carrying a heavy suitcase on his head, and he's walking straight forward along a platform. Now, he's obviously using force to hold that bag up, right? And he's definitely moving forward. So, is he doing any work on the luggage?
this is the perfect example. Let's break it down. What direction is the force on the luggage? It's straight up, right? He's pushing it up against gravity. And what direction is he moving? Forward. So you have an upward force and a forward motion. The angle between those two directions is a perfect 90 degrees. And if you can dust off your old math memories, you might remember that the cosine of 90 degrees is 0, which means the total work done by the porter on the luggage is 0. Nothing. Now, don't get me wrong, his muscles are on fire, he's burning calories, he's doing biological work for sure, but strictly in the physics sense, as far as that bag is concerned, no work is being done.
Okay, so let's wrap this part up. Positive work is easy. You push a box, it moves forward. Force and motion are in the same direction. Negative work is when the force fights the motion, like friction slowing a car down. And zero work, that's our porter, when the force is at a right angle to the direction of movement.
So what do we measure all this work in? Well, the unit is called the joule. And to give you an idea of what that means, lifting a small apple about 3 feet off the ground takes roughly 1 joule of work. So yeah, it's not a huge amount, but it's the basic unit for everything we're talking about today.
All right, so if work is the act of making something move, it begs the question, where does the ability to do that work come from in the first place? And that, my friends, brings us to our next big topic, energy.
The best way to think about it is that work and energy are basically two sides of the same coin. You can think of energy as the cash in your pocket, and work is what you spend it on. Like you eat your lunch to get chemical energy, and then your body spends that energy to do work, like walking up a flight of stairs.
Now, energy comes in all sorts of flavors, but for what we're talking about today, we really care about 2 main types. First up is kinetic energy. That's the energy of pure motion. A moving car has a ton of it. A baseball flying through the air has it. Then there's potential energy. This is stored energy. It's energy that's just waiting to be unleashed, like in a stretched out rubber band or a rock sitting at the top of a hill.
And this is where it all connects so perfectly. There's something called the work-energy theorem, which basically says that the amount of work you put into an object is exactly what you get out in kinetic energy. So if you push a shopping cart to get it moving, the work you did literally transformed into the cart's energy of motion.
Let's zoom in on one type of potential energy for a sec: gravitational potential energy. When you lift something heavy, you're fighting against gravity. You're doing work. But that work doesn't just vanish into thin air. It gets stored inside that object, ready to be released. And the formula is super straightforward. It's just the object's mass times the strength of gravity times how high you lifted it.
Okay, so this idea that energy doesn't just disappear, it gets stored. This leads us to maybe one of the single most important fundamental laws in all of physics. Seriously, it's a rule that governs the entire universe.
And here it is, the law of conservation of energy. It's simple, but it's profound. It says you cannot create energy from nothing, and you cannot destroy it, ever. The total amount of energy in the universe is constant. All that ever happens is that it changes form. It transforms, say, from the chemical energy in a battery into the light coming out of your phone screen.
Let's make this super clear with a simple example. Imagine you're holding a tennis ball as high as you can. Right at that moment, it's not moving, right? So its kinetic energy is zero. But because it's way up high, it is loaded to the brim with potential energy.
Now, what happens the moment you let go? As it falls, that potential energy starts turning into kinetic energy. The ball loses height, but it picks up speed. And right before it smacks into the ground, all that potential energy is gone, and it's been converted into maximum kinetic energy. The total energy never changed, it just swapped hats. And when it hits the floor, boom, that kinetic energy changes again into the sound energy of the thwack and even a tiny bit of heat.
Okay, so we've got it. Energy changes form, but it never disappears. But how fast it changes form is also super important. And that brings us to the last piece of our puzzle today, power. And this is the one that connects all this physics stuff directly to something you deal with every single month, your electric bill.
Simply put, power is all about how fast you do work. It's the rate of energy use. Let's go back to our weightlifter. Imagine two people lift the exact same weight over their heads. They've done the same amount of work. But if one of them does it in 1 second and the other takes 5 seconds, the first person is 5 times more powerful. That's all power is, and we measure it in watts. Yep, like on a light bulb. 1 watt just means you're using 1 joule of energy every single second.
So here's how this plays out on your bill. The electric company doesn't actually charge you for power, how fast you use electricity. They charge you for energy, the total amount you used over a month. And that's exactly what a kilowatt hour is. It's a measure of energy. It means you used 1,000 watts of power for 1 whole hour. So if you have a 1,000-watt heater and you run it for an hour, that's 1 kilowatt hour. You can actually use this simple math to figure out how much any appliance in your home is costing you.
And that brings us right back to the beginning. Work is about making things move. Energy is the fuel you need to do that work. And power is how fast you burn that fuel. But the one rule that ties it all together is that energy is always conserved. So I'll leave you with this to chew on. If energy can never, ever be destroyed, then where does it all go? When you burn gasoline in your car or use electricity to power your life, where does that energy ultimately end up? It's a big question. Thanks for diving into this with me.